All right. So again, thank you all for joining us today. Today's topic is nonlinear analysis in S-Frame. If you haven't attended our recent webinars, I did want to introduce this new format. I'm calling them coffee break webinars. It's basically meant to be a more condensed, succinct version of a presentation that we would have normally done. It opens us up to a lot more topics, as well as it makes it a little bit more palatable for attendees who might not necessarily always have an hour or 45 minutes to spare in their day. So we're going to be pretty strict on, keeping the focus fairly concentrated, and we'll see less slides involvements and more live demos in these types of presentations. This one might be a little bit of an exception. So my name is Matt. If you haven't heard my voice before, I do a lot of these webinars. I've been working with S-Frame and within Altair now the last 3 years, but prior to that, I was with S-Frame for about 9 years. And today's agenda here, we're going to go through a bunch of different examples of applications using nonlinear analysis in S-Frame. And the goal is that we can kind of demystify this. I know a lot of our users might have access to this functionality and don't necessarily know what it could be used for. So we're going to start off with a comparison between different analysis types using a cantilever column, something very simple. Then we're going to look at some nonlinear elements like tension-only members. We'll look at nonlinear quasi-static analysis for rubber bearing support. And then finally, we'll simulate a contact situation with hook gap elements. This is just a handful of examples that we've chosen to demonstrate here. It doesn't by any means represent the whole spectrum of what can be done, but we'll do our best to kind of elaborate as much as we can. So for the first example here, we're going to go through a cantilever column example where we have a lateral load applied. You can see the magnitude. And we're going to compare linear versus nonlinear analysis. And maybe for fun, we'll also add in p-delta static analysis. So I got the model open right here. You can see it is modeled in 3D, but I believe here, if I'm not mistaken, I've restrained the model from moving out of plane. So I've got these default constraints to basically prevent any motion in the y-axis in any of the joints in the model. I've got a fully fixed support. And just to remind ourselves, we have a load at the top, a lateral load only. And this lateral load has a magnitude, if I look at the x-force direction, of 1,000 kilonewtons. The magnitude itself, we're not going to spend too much time worrying about, but I do want to look at the results from different types of analysis. So my first order of operations here is to run an analysis, and I'm going to run a linear static analysis. And if you aren't already familiar with the nuance of that, it's going to assume that the material and the geometric behavior is all linear, and the loads are applied in a static fashion. So they're not changing. It's just basically a static load that's being applied. I'm going to go ahead and run the analysis. I'll click OK. And you can see here we're getting a clean solution. What I mean by that is we're not getting any diagnostic messages, FYIs, warnings, or errors. And what I want to extract from this is just some information related to deflections. So here I can see the deflected shape, which should be of no surprise to me here. I can see here we have a lateral tip deflection of about 2,300 millimeters. Now, this magnitude, take this with a grain of salt. This isn't a real structure, but the magnitude here that we're looking at is something that we just want to make note of. So the top, about 2,350 millimeters. Now I can also look at some additional details, like let's see here, I want to look at the Z displacement. For this example, I don't have any Z displacement, but you can imagine here, if you had a cantilever column and you pushed it to the side, assuming that that column isn't on rollers, you're going to have some vertical deflection as well. But that isn't captured in a linear analysis. We're basically just looking at the pre-analysis stress stiffness matrices and geometry matrices, and looking at what happens when you apply a static load to those with zero incremental updates to the analysis model. So let's just change this up now and say, okay, well, now I want to run a p-delta static analysis. The p-delta static analysis is a little bit different than a linear static analysis. First, it will run a linear static analysis with the loads that we have initially, and it will update the stress stiffness matrices with that stress state of the model. And then it runs a second linear static analysis on the model that has that updated stress stiffness matrices. So we might get some better accounting for p-delta effects, as you can tell by the name, and general second order effects. Maybe not to the extent of nonlinear analysis, but we can see here in just a minute if this makes a difference to our analysis. So right away, when I look at the solution trail, I can see here basically what it's doing. It's running a linear static analysis, and then it's running a p-delta static analysis. And it gets me the results. And once again here, I just want to look at the deflections. That's really what I'm concerned about. And again, I don't see any Z displacement, which that does make sense here. I also don't see any X displacement. So where we might notice a difference between P delta and linear static analysis in this type of model is if we had some sort of compressive force on the column as well. But we don't have that in this scenario, so we're not necessarily going to get that difference. Let's change this up one more time, and we're going to go ahead and run a nonlinear static analysis. There are a few more solution options available to us based on the fact that the nonlinear analysis is an iterative solution. So what it does is it, just like a P delta static analysis, it's going to solve your model. It's going to update the stress stiffness matrices. And it's going to also, something different than P delta analysis, is it's going to update the geometric matrices. So as it deflects, it's going to update, and it does this in an incremental fashion. So we can choose how many static or how many even load vectors we'd like to break our, or increments we'd like to break our load vectors into. In this case here, I said that 1,000 kilonewton load is going to be broken up into 10 even static load increments. So basically, each increment, rather, I apply 100 kilonewtons at a time, update the stiffness matrices, I update the geometric matrices, and then I solve the next iteration, or the next increment, rather. So I'm going to go ahead and click OK to run this. Right away, you'll notice there's more information presented to us. We have all these different load increments, and they take a bit of time to solve, a bit longer than before, because we are basically extending this analysis with 10 load increments. And now when I look at my results, I'm going to start with a dx, my displacement value here. I can see that my lateral displacement appears to have dropped, actually. It was 2,350 millimeters before, approximately. Now it's around 2,000 millimeters. So we're wondering what happened to this. We're still applying the same amount of load, but where the difference lies is actually with the Z displacement. So you can see now I'm getting about 450 millimeters of displacement, which wasn't accounted for in my linear or P delta static analysis. So if I were to actually plot this and compare them, we can see that for this particular scenario, we're getting identical results between linear static and P delta static analysis. But for the nonlinear static analysis, we're actually getting a little bit different behavior. So we're getting less lateral displacement, but more, well, we're getting a non-zero vertical displacement. So as the model deforms, the load that we've applied is still going to be applied to the deformed shape at its original horizontal or vertical orientation, depending on what type of load we have. So what's happening here is this leads to the horizontal load eventually inducing some tension in the column. So this tension can actually increase the lateral stiffness of the column, leading to smaller lateral deformations for nonlinear analysis that actually would mirror the reality. But also, you can see that it's rotating effectively about this base rather than just being applied lateral as if the column can stretch infinitely in that one vertical axis. So it is a little bit more realistic in this scenario. The next exercise we're going to look at is using nonlinear elements. And there's a variety of nonlinear elements in S-frame. I'm not going to touch on all of them. The one we're talking about today is tension-only members. And I think they're probably the most widely used in S-frame. We have compression-only supports. We have tension-only members. We have hook gap elements that we'll look at later. Cables. They can all behave nonlinearly. And their behavior might vary on the application. So if I just go into the next model here, this model is a building structure, and we have a variety of gravity and lateral loads representing wind and dead loads and live loads and so on. And we do have some bracing as well. So right now I've got this folder that's called tension-only bracing. As you can see, I'm just isolating that one folder. And if I look at the member type tool, I can see that right now I'm using truss elements to describe these members' behavior. So trusses are different than regular members in the sense that they can only support axial loads. They have axial stiffness only. There's no ability to withstand any shear or moments. It's purely tension and compression. So if I were to go ahead and run an analysis with this, and I'm just going to run a linear static analysis, I can click OK. And you can see we're getting a clean solution. It solves pretty quick here as well. And if I look at one of my load combination results, I'm going to say dead plus live. I can look at the axial force diagram, and naturally I see there are some axial forces in my columns. I'm going to actually filter this out to just look at my tension-only folder again. And you can see that I have both positive and negative axial loads in this set of members. So positive represents tension, negative represents compression. And a lot of our designers that use SRAM will say, well, I don't actually want to consider any compression in my tension-only members, or my trusses rather, braces, let's say. How can I do that? So there's a way of doing this if you run a nonlinear analysis. And it involves using this member type tool that I currently have active. And you can see here that I'm using truss member types like I mentioned. But actually, we have another option called tension-only members. And I can just simply left-click, oops, dragged a little bit too much with that, left-click and drag my mouse around the members I want to apply this to. And now what happens is, if I go ahead and run my analysis, I'm going to first run a linear static analysis, and we can see what happens. So click OK. And we're getting a diagnostic message. This is an FYI, so it's not necessarily an error. It's just an observation that the solver has made that it wants to share with you. And it's saying, okay, well, you're running a linear static analysis with tension-only members. And tension-only members have nonlinear stiffness, meaning that they have stiffness in tension, zero stiffness in compression. So it can't characterize that with a linear static analysis because it doesn't know if it's in tension or compression until the analysis is done. It needs an incremental analysis to do that. So it's going to convert it to its nearest linear equivalent, which in this case here is a truss. And it's just showing us the FYIs to reflect that. So if I go back and I run a nonlinear static analysis, you can see we have our load increments again. I can click OK. And you can see we're getting a solution. We do get some diagnostic messages. And this is due to the fact that when we have members that are deactivated, if they go into compression, that can cause potential instabilities in our model. And it's oftentimes due to the fact that we have an idealized model that might have purely gravity loads and no out of plumbness or anything like that. So those tension-only members might all be deactivated in some load cases, and it might prevent some stabilities from occurring. But I'm going to look at the results here. And I'm just focusing here on the tension-only member folder again. And I want to look at my axial force diagram. And right away, I can see that in this scenario, only a certain number of my braces are actually being activated. So the ones that go into compression, it's identified they're in compression before the solution has even completed because it's an incremental solution. And it's found, okay, I'm going to assign a stiffness of 0. If it goes back into tension, then it will have a non-zero stiffness. But in this scenario, it's doing this for us automatically here. And I can see for different load cases or combinations, we might get a different distribution of members that are in compression or tension. So imagine doing this manually would be a very time-consuming and finicky process, but the solver here can do it for us automatically. And if you get a large structure with different loading mechanisms and so on, it's not really feasible to do this manually with a linear static analysis. It's going to require you to basically update for every single load condition, and it would require a lot of manual effort just to approximate the behavior. So for this third example, we're going to get even more nonlinear in this. We're going to have a fairly simple frame, as you can see. We've got a portal frame, effectively, and we're replacing one of the supports with a nonlinear elastic curve for rubber. So it's effectively a single node spring with a nonlinear elastic behavior typical of rubber. So this would be a case if we had a rubber isolator, for example, under the right column. And the force versus displacement response of such a spring would look like this next slide here, where basically we describe it when we observe the response, we're going to get a response that looks somewhat like this. So I'm going to go into SRAM again. And in the model that I'm looking at here, very simple from the outset, we can see here that we've got a nonlinear spring. So I'm using the nonlinear springs tool to assign this 1 degree of freedom's restraint. So this is the Z direction, Z translational direction. And you can see I have this rubber function, this nonlinear spring function to describe that behavior. And I can actually right click on this nonlinear spring, and I can see that it allows us to define both bilinear springs or multilinear springs. And in this scenario, I've got this rubber curve to describe that, that spring. I'm not going to worry about modifying it right now. You can describe it in a text file effectively, like a spreadsheet, and you can assign it to a degree of freedom, and then we can run an analysis. So for this scenario here, I ran a nonlinear quasi-static analysis. And basically, what that allows us to do is it operates very similar to a nonlinear static analysis, but it allows us to sequence our loads in a specific way. So what I've done is I've applied a load, and you might recall here from that little diagram I showed earlier, we have this 2,500 kilonewton load applied just to this one location above the column. And I've applied this quasi-static curve or function. So I got this, this tool right here that basically what it's doing is it's saying that 2,500 kilonewton load at time equals 0 is going to have a magnitude of 0 or a scale of 0. And then it's going to linearly increase in magnitude until it reaches its full 1.0 magnitude or scale factor. And that's around time of equals 4 or 5 seconds. I think it's 4 seconds in this scenario. And then it's going to be held steady for a second, and then it's going to unload in a similar fashion. And it's basically meant to stress this rubber bearing and unload it again. I've already ran the analysis. Again, it is a nonlinear static or quasi-static analysis. So we set up time step size and the number of time steps we want to run and let the analysis solve for that load sequencing that we've done. And I can go here to the graphical results window now. And if I just right click on this, this joint, because I've already got the solution completed, I can right click on this joint here and I can look at the response time history or the pushover curve, and I can see what's happened for this particular joint. So this is showing me, in this case here, displacement versus base shear. And it's showing me in the x-axis, but that's not the direction of loading. I want to look at the z-axis. So here I can get to see the behavior described a little bit more clearly to me. And we can, it's subtle, but we can see differences in the deformation curve as we increase the base shear and unload it again. So we're just applying this base shear in one single direction, but as we described earlier, it can also be enacted in a similar way if we were to pull this up rather than push it down. So we're only seeing half of this curve essentially. And I think I've got in my slides a little video that shows the SView animation of what this looks like as well. So let me just render this for you. So here, this is the joint, and it's subtle again, like I mentioned, but if you really pay attention to this, you can see it accelerating kind of partway through the loading and then decelerating as it gets to the bottom or top of that loading function. And there's lots of different applications for quasi-static analysis beyond just, testing this type of nonlinear material. I think this is just the most tangible from a visual perspective, but I use it often for when I want to sequence different loads. So maybe I want to apply a gravity load onto a structure and then ramp up a vertical load, like a pushover analysis, for example, can be accomplished through this type of analysis and loading functions. For our last exercise today, we're going to look at a simulation of a contact condition. So we've got two adjacent frames. As you can see here, I've got basically they're right next to each other, and there's a small gap between these. And I'm going to assume here that between these two nodes, we can look at a condition where there is contact between these two nodes and where there isn't. And what I'm going to do is I'm actually going to apply a harmonic load, or a seismic load rather, to the frame on the left, and observe two different scenarios, one where they're connected, one where they are disconnected, and we'll be able to see what happens there. So I believe this is the first example. If I just zoom in here, because the models look identical, I've lost track. This is the one that has the link, so I'll come back to this one. But let me go to this one instead. Is this the right one? My eyes are playing tricks on me because the models are zoomed in exactly the same amount. So this isn't the one I had intended here. This is the first one I'll start with. So effectively, as we zoom in here, we can see that there is a gap between those two locations with nothing connecting them. And what I've got in this model is a time history load. So the time history load is described with a accelerogram, where I'm using this Cape Mendocino accelerogram, or accelerogram, base motion record, to describe the support excitation just on a few of these joints. So basically just on the supports underneath this column on the left-hand side. And there is no linkage between this frame and the frame next to it. So naturally, I'm sure you could guess, we shouldn't observe anything happening in the frame to the right. It's kind of like those mattress commercials where you see two isolated mattresses and you can sleep next to your partner without disturbing them. That's the analogy I'm using today. So I've already ran the analysis, and what I did was I ran a linear dynamic time history analysis, and I'm using variable time step integration. We got a lot more information on this. You don't have to learn it all today. But you can see here that we're basically describing an initial time step size, and then we're giving it a window of time step sizes because what happens is we're sampling the response at discrete points within that loading curve and observing the response of our structure to that loading curve at these discrete points. So this variable time step integration can actually vary when we take the time step measurement in order to optimize the analysis efficiency. So if there's not a lot happening and the acceleration isn't changing very much, it's not going to sample the response there because it's a waste of time. You're just getting a linear response at that point. But it does a really good job of kind of optimizing the computational resources without having to extend the analysis time too much. So what I can see here, I'll just take a couple maybe example points here. So I'll just say for this point in the middle of this beam, I'm going to look at the response time history. So this is my input ground motion. And this is my time history response. So this is the acceleration in the x-axis versus time. And I can see the acceleration on that joint as well as the displacement. And we get an idea for, we're getting about 16, 20 millimeters of displacement, perhaps at maximum about 18 millimeters in this frame. The frame next to it, we should see 0. So I can right click here, go to response time history. And for the time history response, again, I don't see any displacement or any acceleration. That's in line with my expectations. Going back to my previous model, here we've got this little link in between the two models. And if I go to the geometry window, I can actually see that I'm with the member type tool that I used earlier to define those tension only members. We have another member type called an elastic plastic link beam. And I'm using that to describe essentially a hook gap element between these two parts. And I can right click on the member type tool to dive a little bit deeper. So for the elastic plastic link beam, here I have what I'm calling a contact element. And basically we've got a gap that we've defined of 5 millimeters. And so when that gap is, when the deflection between these 2 points is less than 5 millimeters, there's going to be no resistance from that, that gap element. But once that gap element's threshold of deflection has been achieved, 5 millimeters, so if we have more than 5 millimeters displacement, we're going to have some resistance from that gap element, and I've given it an arbitrarily high stiffness in this scenario. Now, I've already ran the analysis again just to save a bit of time since we want a few examples to get through here. So I go to the graphical results window, and we've already seen here what happens in the frame on the left, but I'll just remind ourselves for this time history analysis here. This is our input ground motion. This is our response for the frame on the left, acceleration and displacements. There might have actually been a different ground motion now that I think about it, although I suppose it's being influenced by what's happening with the frame next to it. But you can see here what's happening fairly clearly. There is pretty constant acceleration and displacement in this frame because it is being loaded with those time history loads, and the supports are shaking. The frame on the right, though, is where we're really more interested. And I can go to right click, response time history. And in the time history response, we can see there's very distinct points where the acceleration is spiking and it's pretty much 0 in between. So that's showing us that those flat areas are probably where we have less than 5 millimeters of displacement. And there's really not much in the way of any influence from the neighboring structure. The displacement will see a little bit more constant behavior. We do have some damping in the model, but it will naturally dissipate a little bit with our Rayleigh damping coefficients. And this might be best illustrated through 2 separate animations here. So this is the animation of the model without the gap element, if I remember correctly here. Oh, this was with the gap element, so you can see them kind of shaking together. But there are some times where the model on the left will move without its neighbor. At least a little bit more dramatically. And then I would say at this point it's probably a little bit non-dramatic, but on the bottom model, we can see that there is clearly no connection between the two. So hopefully that was illustrated through those graphs we saw earlier as well.